Hi, how you doing? So trigonometry, yes, trigonometry, one of the greats in the mathematical universe. Okay, I'm going to talk to you about trigonometric identities today. You may have seen this, so it's just a reminder really as to where the sine graph can be generated from. So you take the unit circle, which means it's got a radius of 1, and if you measure it in radians, the unit circle is measured from 0 all around to 2 pi radians. Okay, always taking the positive x-axis as the starting point and then go in an anti-clockwise fashion. Well, if you trace a point around that unit circle from 0 to 2 pi radians, then you can plot it on the same set of axes as a sine graph like this. Okay, so this time we have the horizontal scale being the angle between 0 and 2 pi, and the y-axis, the vertical scale, is still the height of a particular point above the circle relative to the x-axis. Okay, that's just a reminder. Why am I showing you that? Well, it's because it's helpful in talking about the identities. Okay, so for the identities, I'm going to have another circle, this time call it radius r. That means I'm not just talking about a unit circle now with radius 1, I'm talking about a radius where you can have any value, it's more flexible. Okay, so you've got a circle and the radius is r. Still pick a point on that circle, we can still talk about this particular point as having coordinates x, y, okay? So that would be the x coordinate, that would be the y coordinate. Now you remember your simple trigonometry with right angle triangles when you learnt it for the first time? You should remember that, of course. So in this right angle triangle, the cosine of that angle is the adjacent over the hypotenuse, isn't it? So we can say the cosine of theta is x over r. Or if you rearrange it, you can say that x is equal to r cosine theta. And the sine of that angle is opposite over hypotenuse, so y over r. And so you can say sine theta is y over r, or rearrange it, y equals r sine theta. And of course, tan theta, opposite over adjacent, tan theta, y over x, hence written it there. Now we're going to use those results to come up with the trigonometric identities. Remember Pythagoras Theorem? X squared plus y squared equals r squared? Yeah, hence the equation of the circle. You see, x squared plus y squared equals r squared, okay? So obviously it's linked together with Pythagoras theorem with the equation of the circle, centre of the origin, I might add. Now, what happens if we put those two into that? I'll show you. You end up with this result, okay? You end up with r cos theta all squared plus r sine theta all squared equals r squared. And I'm going to use that to generate our first trigonometric identity. Now, when you remove the brackets, you end up with this. Now, let me just talk a bit about the notation there. When we say cos squared theta, cosine squared theta, written like that, we really mean the cosine of theta all squared. Okay? You just got to get used to this notation because powers of trigonometric terms comes up a lot in mathematics. So you might be talking about cos cubed x, cos to the power 4x, cos to the 5x, cos to the nx. You just got to realise that really we're talking about this. And because it comes up so often, we don't use this because basically it's longer to write down. So someone came up with this handy method of making it simpler for us to write down. So cos squared theta is the same as that, okay? And hence r squared sine squared theta. And that's the way we say it. We say sine squared theta. And so you've got that plus that is equal to r squared. Well, what can we do with that? We can either divide that by r squared, of course, r not being 0, or you can factorise first. So you get r squared, cos squared theta plus sine squared theta equals r squared. Well, that being the case, cos squared theta plus sine squared theta must be 1, mustn't it? Okay, because r squared times that has got to be r squared. So the brackets has got to be just 1. So that gives us our first trigonometric identity, a very handy identity indeed. Cos squared theta plus sine squared theta is equal to 1. And for the second identity, we're going to go back to this again. So y over x is equal to tan theta. So putting them together, you've got that result we had, y over x equals tan theta. And also, if y is r sine theta and x is r cos theta, you can just put the two together and say that these must be equal. So you've got tan theta must be the same as that. And of course the r's will just cancel. The r's will cancel. So you're left with sine theta over cosine theta. And that's our second identity. Tan theta equals sine theta over cosine theta. And there we go. Okay, there we go. You'll find those identities extremely helpful. I should just add, it's important you recognise that this angle theta represents the same angle at all times. Let me just give you a simple example of that. Okay, if I just get rid of this. let's just choose an angle, okay? And because I've been talking about radians, let's choose an angle in radians. So let's just choose the angle pi over 6. That's a nice one, isn't it? 30 degrees, pi over 6. So if you were to work out the cosine of pi over 6, what would you get? Yes, indeed. You'd get the cosine of 30 degrees, which is root 3 over 2. Okay, so I'm going to write that here, root 3 over 2. Now, what would cosine squared pi over 6 be? It would just be that squared. Okay, so I'm going to write down for a moment that squared. Okay, and then we'll do the same with sine. Okay, so sine pi over 6 or sine 30 degrees. What's that going to be? Yeah, it's going to be a half. And if we square that, sine squared, we're going to get 1/2 squared, aren't we? And you can just check that when you add these two together, you do indeed get 1. You do indeed get 1. Because that there is just going to be 3 over 4, 3/4. That would be 1 over 4, 1/4. 3/4 plus 1/4 is 1. So that's just a showing you scenario, a showcase that this identity does work. It does work for every single angle, whether it's degrees or radians. It doesn't work when you've got different angles. So you wouldn't be able to do it if you had sine squared pi over 6 and cos squared pi over 4 or something like that. Okay, the angle's got to be the same. Same with this as well. Okay, you can easily check that the sine of pi over 6 divided by the cosine of pi over 6 gives you the tan of pi over 6. So the sine of pi over 6 is just a half. The cosine of pi over 6 is root 3 over 2. Half divided by root 3 over 2, 1 over root 3. Okay, and the tan of pi over 6 is also 1 over root 3. So just some examples then. You can check it yourself if you want, using some more obscure angles in degrees or radians on your calculator. Okay, right, coming up will be some examples on how we can use these identities to solve some mathematical problems. Alright, so here's a really nice example showing you where we're going to make use of what I've just been talking about. So this is a show that question. What I mean by that is we need to show that one side is equal to the other. So there's no equation there where we need to solve something or find out a particular angle or something like that, okay? We need to prove that this identity simply works, okay? And we've got the left-hand side is cos squared theta plus 3 sine squared theta, and the right-hand side is 3 minus 2 cos squared theta. Basically, we've got to show that they're exactly the same thing, okay? And the thing to do is you pick a side on which to start. Most often, the side to begin with is the left-hand side, LHS for short, okay? And I'm just going to write out the left-hand side again. So cosine squared theta plus 3 sine squared theta. And the idea is that with each new line of working, I'm going to simplify that as much as possible and work my way towards the right-hand side. Okay, that just gives you a clear method, a clear structure as to how to go about answering one of these problems. Okay, now what we'll notice is on the right-hand side, there's no sine terms anymore, it's just cosine terms. So the identity we want to use is to try and get rid of that term and write a cosine squared term instead. Can you see which identity we're going to use? We're going to make use of this one. Cosine squared theta plus sine squared theta is equal to 1. We're going to make use of that. And in making use of it, we can rearrange that identity. Okay, we can rearrange it. I can make sine squared theta the subject. The sine squared theta is 1 minus cosine squared theta. And I'm going to substitute that in. Okay, I'm going to substitute that in. So the next line is going to be cos squared theta plus 3, and because I'm substituting in, I'll put in brackets 1 minus cos squared theta. Now I'm almost there, you see, because my expression is all in terms of cosines, which is what I want for the right-hand side. I just need to expand the brackets, so that'll be my next line. So cos squared theta plus 3 minus 3 cos squared theta. I need to simplify by bringing all the terms together, so that subtract that is going to be negative 2 cos squared theta, but I'm going to write it as 3 and then the negative 2 cos squared theta like this. And I'm going to check that's what I want. Yes, it is. And I can conclude by saying that is equal to the right-hand side, RHS. And then I'm done. And that is your format for solving one of these problems, okay? I'm hoping that made sense to you. Before I go to the next question, can I just point out something. See the symbol there? That is the identity symbol, okay? Strictly speaking, you're supposed to use that every time you use an identity. So strictly speaking, this should also be an identity symbol as well, as should this, as should this. It's just that, well, let's be frank, I do these questions quite a lot, and this is one of the things that I just generally stop doing, okay? Stop using the identity symbol. Why do I stop doing that? Because when I'm solving an equation, I'm usually using the equal sign, and I don't think it's appropriate to use an identity sign within an equal sign. Sorry if that offends you. If it makes you feel better, just go ahead and put all the identity symbols in. You just have to write this, and then it would be much more mathematically accurate to do so, okay? But forgive me if I'm not putting the identity symbol in, I'm just writing equals, okay? Right, on with the next example. Okay. Wow, that looks a bit harder, doesn't it? Okay. I'm just wondering whether I've got enough board space, okay? Because I've not had a go at this one yet. So what I'm going to do is, maybe in anticipation of having several lines of working, I'm going to just rearrange my board a bit, okay? So I'm going to start with the left-hand side, okay? Now, that might seem obvious, but sometimes the right-hand side is the place to begin, okay? What I normally go for is the side that looks the most complicated, because then I can try and do something with it, see? I can normally simplify it, okay? Now, we'll start with the left-hand side. Now, because I'm not sure how much work this is going to take, I'm not going to just rewrite the left-hand side again. I'm going to assume that you're happy for it to be that, and I'm just going for my first line of working. What I'm going to do is I'm going to expand the brackets, okay? That might seem like a sensible place to begin. I'm going to expand the brackets. So this one here will be 1 plus 2 sine theta plus sine squared theta. And this bracket here, when I expand it, that's going to be 1 subtract 2 sine theta plus sine squared theta. I've not forgotten about the denominators, no. But what I've noticed is that the denominators are both the same, cosine theta, which is rather handy. It's handy because I can actually write all of this as one fraction, and I'll have cosine squared theta on the denominator, okay? Right, next line. I'm going to simplify that. So I've got 1 plus 1, which is 2, okay? Nice bit of mathematics there, you'll notice. 2 sine theta, subtract 2 sine theta is 0, they cancel. And then that plus that, I'm going to have 2 lots of sine squared theta. So plus 2 sine squared theta. And that's all over cosine squared theta. Okay, happy with that? Right, next, I can factorise if I want, but that's not really helpful, is it? I want to try and see how I'm supposed to get that. It's looking a bit difficult, isn't it? Because I'm supposed to end up with tan squared theta, which is fine. Can you see I've got that? Sine squared theta over cos squared theta is tan squared theta. But the trouble is that's 2 tan squared theta plus 2. I'll tell you what, I'll write it down anyway because I've got nothing else to do. Okay, so that's going to be 2, and that's over cos squared theta plus 2 tan squared theta. Okay, now what can I do with this? What can I do with this? I could use an identity from year 13, but that's a bit cheating, isn't it? Okay, that's what I would normally do. But bear in mind, if you're watching this, you're probably in year 12. I'm not going to do that, okay? But I would use identity for sec squared theta. I'd use tan squared theta plus 1 equals sec squared theta. Let me just write that down for you. Sec squared theta is equal to 1 plus tan squared theta, you see. And then I'd have 2 sec squared theta, which is 2 times 1 plus tan squared theta. And then when I add it to that, you can see the 2 plus 4 tan squared theta. Okay, but since you're probably not in year 13, I'm not going to do that one. So I'm going to come up with something else, okay? So what I'm going to do is, okay, I'm going to insert here the number 2 as 2 lots of sine squared theta plus cos squared theta. Okay, and just see what that happens. Okay, see what I can do with that. So that's all over cos squared theta. Okay. See, what I can now do is I can combine that and that. Yeah, 2 sine squared theta plus 2 sine squared theta is 4 sine squared theta. So that would be plus 4 sine squared theta. Sorry, that looks a bit dodgy. And then I've got the 2 cos squared theta there. So I'm just writing it like this. And that's all over cos squared theta, of course. And can you see where I'm going with this? Right, next, 2 cos squared theta over cos squared theta is 2, which is that. So it's looking good, isn't it? And then 4 sine squared theta over cos squared theta is just that. Okay, so plus 4 tan squared theta. I'm not sure if I've mentioned it, but if you remember the identity from before, tan theta is sine theta over cosine theta. Well, obviously, I hope it's obvious. If you square both sides, you end up with this identity. Tan squared theta is sine squared theta over cos squared theta. Okay, hence that over that is tan squared theta. And I've run out of space, as I kind of predicted, but that, of course, is equal to the right-hand side. I would love to be able to put that underneath, but I've run out of space. Okay, so that's how you do it for year 12. But as I said, once you're in year 13, you would actually use that identity there. Where does that identity come from? Maybe just have a think about it. Maybe just look it up. Okay, I'm not going to tell you though, because it's year 13. Or maybe as an extra at the end of this video, I'll fill you in with that. You just have to keep on watching to find out, won't you? Okay. Right, next example coming up. Okay, here's my next example. Now, to be perfectly honest, I really don't like these. I just don't like them, okay? It's the one thing in trigonometry that I just really don't enjoy doing for whatever reason, okay? I mean, don't get me wrong, it's still a load better than statistics, you know, or decision maths or things like that, okay? But in terms of the whole trigonometry unit, I just don't like questions like this. Give me an identity, give me an equation, give me a graph. Yes, all of those. But one of these, no thank you, okay? It takes the fizz out of trigonometry a little bit, okay? But it's there in the syllabus and you kind of got to know how to do it. So let's go ahead and do it, okay? It's still maths, so it's still great. It's just not the best thing you could do with trigonometry. Right, so given that sine theta is 3/5 and that theta is acute, find cosine theta and tan theta, okay? Well, what you could do is just pick up your calculator and work it out, of course. But you're supposed to be able to do these without a calculator. And there's several ways of doing it. I'm going to show you my preferred way of doing it, okay? What I'm going to do is I'm going to draw out a right angled triangle like this. And I'm going to assign theta to be that angle there. Theta is acute, so that kind of makes sense, okay? And then if sine theta is 3/5, then I can just assign that to be the opposite and that to be the hypotenuse. See how that works? Opposite over hypotenuse, 3/5. And then I can use Pythagoras Theorem to work out that. It's a Pythagorean triple, so that would just be 4. Now I can work out my answer from that. Simple. So cosine theta is 4/5. Right, I'll write it in here. Adjacent over hypotenuse. And tan theta is just 3/4. Opposite over hypotenuse. And that's it. It's done. Okay, that question is done. There is an alternative. I did say there's an alternative. What's the alternative? Okay, well, the alternative is you could use this identity here. Sine squared theta plus cos squared theta is equal to 1. And because you know what sine theta is, you can put it in. So sine squared theta will be that squared. 3/5 squared is 9/25. So 9/25 plus cos squared theta is equal to 1. And then if you just put this onto that side, you'll have cos squared theta is equal to 1 subtract 9/25. That's 16/25. And then you just take the square root of both sides. The thing is, in doing that, do you consider both positive and negatives as your answers, okay? Is it possible that you could have positive or negative 4/5, okay? Well, that's when you just go and look at the graphs and decide which one of those it could possibly be, okay? Or you can use your cast diagram, but I don't like cast diagrams, if I'm totally honest with you, okay? Well, if you look at the cosine graph looks something like this. Let's put it in degrees just to help you out a little bit. So you've got 0, 90, 180, 270 and 360 degrees. Let's just finish labelling up. There we go. Whoops, what am I doing here? That'll do, Y and X. Okay. So we've got The sine of a number is 3/5, okay? Well, the inverse sine of that, what's that going to be? That gives you an acute angle, which means it's got to be positive, okay? And if you take the cosine of a positive acute angle, look, here, if you take the cosine of an angle between 0 and 90 degrees, you'll get some number between here and here. So it's impossible for the cosine of a number that's of an angle that's acute to be negative, okay? So you just have the positive 4/5 as your answer, okay? Now this is a fairly straightforward example because theta is acute. Let me show you another example when the angle is not acute, and then we'll see why that's a little bit more challenging. You ready for it? Here it is, okay? So this time cosine theta is negative 3/5 and theta is reflex. I don't think the angle, so the fraction's coming out nicely there. Let me just make it a bit better for you. There we go. Right, and theta is reflex. So if I use the same approach, here we go. Whoops. Let's try it again. There we go. Right, if I use the same approach, that is not a reflex angle, is it? No. So I'm going to call that alpha instead, not theta, because theta's got to be reflex angle. Okay, and I'm going to ignore the negative, all right? But I'm going to go for adjacent over hypotenuse again. So 3/5, and that's got to be 4 because it's basically the same 3, 4, 5 triangle. Okay. Now if I use this, I'm going to have sine alpha is equal to 4/5, and I'm going to have cosine alpha. Well, I've got that already. Is negative 3/5. I won't write that down again. I'll have tan alpha is equal to 4/3. Okay. However, because theta is reflex, it may be the case that sine theta is negative 4/5 or positive 4/5. We don't know. Okay, we don't know. Right, second method then. Maybe we use the identity. Okay, sine squared theta plus cos squared theta equals 1. So we're going to have sine squared theta is equal to 1 minus cos squared theta, and cos theta is that. So square that, you get 9/25. So sine squared theta is going to be 16/25. So sine theta, and similar problem again, we're going to get positive or negative 4/5. We're not sure which way it is, okay? Basically, the whole idea of theta being reflex makes it a little bit harder, okay? It's a little bit more challenging. The thing to do is this. Pick up your calculator. That's the thing to do, all right? Now, I'm just going to put it into degrees mode. I'll suggest you do the same because, well, let's face it, when you're dealing with degrees, it's just a little bit more manageable, isn't it, okay? And we're going to work out what the angle actually is, okay? So I'm going to type in inverse cosine of negative 0.6, negative 3/5, okay? Right, I get 126.86 degrees, okay? 126.8698 degrees, okay? Now, is that reflex? No, of course it's not reflex, okay? So that's not the angle I want. How do you find the angle that is required? Well, you need to subtract from 360 degrees, okay? If you're not happy with that, go to the video I talk about solving equations. That'll make it a lot clearer for you, okay? But you subtract from 360 degrees. So if I do 360, subtract that value, yes, I've got it. I'm just going to write that down, make a note for you. So I've got 233.13 something degrees, okay? That's the angle I'm looking for, and it is reflex. I'm just going to work out the sine of that angle now. Okay, so sine of that angle, voila, gives it to me. Yeah, a bit of French in a trigonometry lesson. Okay, should be speaking Greek really, shouldn't I? Because trigonometry is from the Greek mathematicians. Trigonometry, although the pronunciation is not great. Okay, so negative 4/5 is what I get on my calculator. So what that means is that sine theta is negative 4/5. Okay. Now, you might ask, well, why don't you just do that from the beginning? Yes, you could do, okay? The triangle method is just so that you get the correct fraction, because sometimes you get awkward numbers and the calculator's not really that fond of being able to do it exactly for you, okay? Sometimes they come out as decimals and you want them as exact values, all right? Now, you could do exactly the same again to work out tan theta, but let me show you an alternative, and one that I didn't mention in the previous example, but I suppose I could have done. Now, you can work out tan theta just by finding out what sine theta over cosine theta is. Yeah, just using that identity. Yeah, so you've got sine theta now as negative 4/5, and you want to divide that by negative 3/5. Obviously, a negative divided by a negative is a positive, and the fifths will cancel, so it's just going to be 4 over 3, positive 4 over 3. So your tan theta is positive 4 over 3. Okay. All the thing to do is just to work out what that is again. So just get it up. There we go, 233.13 degrees. Work out the tan of that angle, and yeah, confirms it for you. It is 4 over 3. Okay. So yeah, I mean, why don't I like those as much? Yeah, there's a bit of logical thinking behind it. It's some mathematics, it's trigonometry. It's just not as challenging for me personally as doing an identity question or a solving an equation question or drawing graphs. I do love graphs. Okay, hopefully you do too. Anyway, more examples coming up. Right, next type of examples. I do love these. These are what we call parametric equations. Now, if you're in year 12, it probably doesn't call them that in the textbook, but believe me, these are what we call parametric equations. In the textbook, it probably says something like eliminate theta from the following pairs of equations, okay? But what they really are they are parametric equations. So what are parametric equations? Well, they're equations, but with a third variable involved. So normally you've got x and y, and if it's only x and y, plus some other numbers, some constant values, yes, but if it's normally x and y, they're what's called Cartesian equations, named after, yes, René Descartes. Okay, fantastic man, okay, a mathematician. But these ones, they're called parametric equations. It's got a third parameter involved, okay? Now, what we often want to do is convert these parametric equations into Cartesian equations. And the method for that is to eliminate this third variable, in this case, theta. So it's a little bit like simultaneous equations, okay, except we're going to end up with one equation involving just two variables instead. Now, the thing to do with these is to use an identity. Use an identity to try and eliminate the trigonometric term. And the identity we're going to use here is sine squared theta plus cos squared theta. Now, what we'll do is we'll square both of these. Maybe in dealing with equations or simultaneous equations, you've not tried squaring both sides, but you can actually do that, of course. And on the first equation, you get x squared equals cos squared theta. And the second equation, if you square both sides, you get y squared equals sine squared theta. Now we're going to add the two together. Okay, we're going to add that equation to that equation there. And what happens when we add them together? Well, let's write it out. We'll get x squared plus y squared on the left, that plus that. And on the right hand side, we'll get that plus that. Cos squared theta plus, whoa, missed out the theta, plus sine squared theta. And of course, you can see how that simplifies. Cos squared theta plus sine squared theta is just 1. So now we've done it. You see, we've done it. We've rewritten the equation without the variable theta. And that is what's called a Cartesian equation. Yes, a Cartesian equation. What's that the equation of? Of course, it's the equation of a circle. And we'll just remind you about that. So here we go. So here's our circle, okay? And generally, the parametric equations of a circle are given as this. X equals r cos, you can use any variable you want. Here it's written as t plus a, and y equals r sine t plus b, okay? And here's a lovely GIF, it's called, of some satellites orbiting the Earth, okay? I think it's about docking and the ISS, okay? It's all fascinating stuff, all right? Maybe you've come across that equation, okay? You probably have in year 12 and you've got this far, okay? So that's the equation of a circle with centre A, B and radius r. This is the equation of a circle in parametric form, okay? Let's just go with this, okay? What I'm going to do is I'm going to just adjust my board a little bit. Maybe let's just get rid of that, okay? Even though it's really, really nice. Let's just prove, shall we, that these are the parametric equations of a circle. So we're going to do the same thing again as what I just did. So we're going to eliminate theta from these two equations, okay? So what I'm going to do is I'm going to make cos t the subject, okay, in the first one. If I subtract a and then divide by r, that will give me cos t the subject, wouldn't it? So I'm going to have x subtract a all over r, okay? And for this one, I'm going to make sine t the subject. So sine t, that's going to be y subtract b all over r, okay? I've not thought about this, but the writing white on a black background is actually quite nice, isn't it? I quite like it, this, okay? And then you just go square those and add them together, okay? So you've got cos squared t plus sine squared t is equal to 1, of course. So you've got that squared plus that squared is equal to 1. So you can write it as x minus a squared over r squared plus y minus b squared over r squared, and of course that's equal to 1 because sine squared plus cos squared is equal to 1. And then you can multiply both sides by r squared, and that's when you end up with that, you see. So that's a demonstration for you as to why those parametric equations give you the equation of a circle. I'm hoping you enjoyed that. Right, let's go back to these again. Right, here's the next example. This is pretty easy now, isn't it? After the one I've just showed you, this is a pretty easy one, okay? The method is the same. You just make cos t and sine t the subject in each case, okay? So in the first case, make cos t the subject, you have x minus 2. Oh, I'm trying to write white on white now. Let's go for black on white, okay? So cos t is x minus 2. And then here, sine t is y plus 5, okay? Then we're going to square them both. So you'll have, whoa, there we go, that squared and that squared. Then we'll add them together, there we go. And of course that's equal to 1 because sine squared t plus cos squared t is equal to 1. That's it, done. The equation of another circle, centre 2, -5, radius 1. Okay, let's do one more, shall we? Here we go. Same sort of thing again. Make sine t the subject, so you'll have x over 2 this time. Make cos t the subject, you'll have y over 3 this time. Square them both, there we go. And then add them together, and that's equal to 1. If you want to expand the brackets, you can do so. X squared over 4 plus y squared over 9 is equal to 1. Is that the equation of a circle? Is this the equation of a circle? No, it's not, okay? This is not a circle, okay? It's actually an ellipse. Why is it an ellipse? Well, you can actually work out what the extremes are in relation to the origin, okay? So, for example, when y is 0, you can work out what x is, where it crosses the x-axis. So when y is 0, for that to work, x has got to be 2 or -2, because obviously 4 over 4 is 1. So 2 or -2. So either there or there, okay? And then do the same again for this. When x is 0, what is y going to be? Okay, where's the y-intercept in other words? So y has got to be 3 or -3. So 9 over 9 gives you 1. So 3 or -3, there or there. So you can see, just because of the extremes there, it's not a circle. It's actually an ellipse that looks a little bit like this. So not very well drawn from me, but you've got an idea. Generally, an ellipse looks like this, okay? And let me just write this a bit bigger for you so you can see the fractions. There we are. Don't know what it is about this board, but sometimes the vinculums don't come out clearly. Okay, so here we go, that's the general equation of an ellipse. The idea is, if those denominators are different, it's not a circle, it's an ellipse. Okay, if those denominators are the same, if you've got a is equal to b, you could just multiply throughout and you've got the same equation as x squared plus y squared equals r squared. Okay, this is an ellipse, and the general parametric equations are those. Okay, well, I'm hoping you found those examples in parametric equations rather fascinating. Okay, that is it. I'm hoping you found those examples really helpful too. If these are the first two identities you're learning, then great, you're on your way, because believe me, there's plenty more examples to come in year 13. Okay, maybe depending on when you're actually viewing this, those videos have already been created and uploaded. Okay, but if you're viewing this kind of soon after I've made it, you'll probably have to give it maybe a year or something like that before those videos are available. Okay. Right, I'll see you again soon. So it's not quite the end. I did say to you that maybe I'll put this at the end of the video, and yes, I'm going to do that. So you remember this example? I said I might indicate where that comes from. Well, let's just go ahead and do that, okay? It's very quickly done. So making use of the identity sine squared theta plus cos squared theta is equal to 1. What we can do is we can divide both sides of that by anything as long as it's not 0, okay? So I'm going to divide both sides by cos squared theta. And what do we get? What do we get if we divide by cos squared theta? We get sine squared theta over cos squared theta plus cos squared theta over cos squared theta is equal to 1 over cos squared theta. Okay? And if I simplify that, that over that is tan squared theta. Okay? Tan squared theta. And then this is just 1, and then this, well, that is sec squared theta, where sec theta is another way of writing the reciprocal of cosine theta. Okay? You don't need to know that really. This is more year 13, but I'm just jumping ahead, and some of you might have been interested in that result. Okay? You can also come up with another one. Okay? I'm not going to give it to you, but if you wanted to, of course, you could divide both sides by sine squared theta and write down another appropriate identity. Maybe you do that and then do a search on the internet, just see if you got it right. Okay? I'm hoping you found that useful.